who is a research manager at Allen AI Tube, Allen Institute for AI. And Roozbehm is also an affiliate associate professor at the University of Washington. So I think Roozbehm and I actually, we have some overlap because I was also once a research intern supervised by Professor Alan Yu, now at Johns Hopkins University, while Roozbehm is also Alan's PhD student. And okay, so looking forward to Roozbehm's interesting talk.
Okay, thanks for the introduction. I'm going to share my screen. Okay, can you see my PowerPoint?
Yes.
Okay, great. Hi, everyone. Let's get started. Okay, so here is a typical computer vision pipeline. So there is data that's fed into a model, and there is a training algorithm that trains the model for a specific task. For example, we have ImageNet, and we use the data to train a standard convolutional neural network, such as ResNet, using a stochastic gradient descent and cross-entropy loss to perform a specific task, such as image classification, to distinguish different types of objects, for example. But let's compare this pipeline with a real-world example, with a real-world scenario. So this kid probably has never walked in the rain, and keeps falling, but he learns to adjust his moves, and finally he manages to walk over the puddle and come to the other side. So let's compare this scenario with a typical computer vision pipeline. So let's look at the data first. So there's no supervision in real world usually. Nobody tells the kid how to move the feet, how to adjust the moves, and so on and so forth. And there is no fixed data set. For example, we don't tell the kid, here's your training set, go learn how to walk, and then we will evaluate you in a test set. And also, there's no cleanup. So we have a large amount of data. Some part of the data is relevant to us and relevant to the task, and some part is not relevant. And even the part that's relevant to us, to our task, might be noisy. Okay, let's look at the model and the training algorithm. So there's no boundary between training and testing and training happen simultaneously. And the kid learns to perform, learns about the task as he performs the task. Also, we need to learn from dynamic data. So our environment keeps changing, and we need to learn from that. And sometimes we need to learn or we need to adapt according to a time constraint. So there is a specific budget, and we have to learn within that budget. Okay, and the tasks. So most of the tasks that we address in computer vision are passive tasks, meaning that there's a fixed training data, there's a fixed test data, and these are tasks like classification, detection, pose estimation, and so on. But in reality, so we have these interactive tasks. So we receive streams of data, and at every second we encounter new situations, and we need to make decisions about this, about the new data that we encounter. Okay, so we are facing new challenges in interactive AI. In this talk, I'm going to focus on embodied AI as a form of interactive AI, and my focus will be only on the tasks. So I'm not going to talk about data and models. So I'm going to talk about tasks in embodied AI. So in the past couple of years, we have had good progress in many different problems in embodied AI, such as navigation, visual planning, question answering, multi-agent collaboration, occlusion reasoning, time-sensitive planning, and so on and so forth. Last summer, a number of us got together, so we come up with a clear task definition and a unified set of metrics for a specific task that we call rearrangement. So the report has been published on arXiv and in November last year. So here is the explanation of the task. So on the left, you see the goal state, the image of the goal state. On the right, you see the current state. And the task is to take a sequence of actions. There is an agent that needs to take a sequence of actions to convert the current state to the goal state. For example, in the current state, the toaster is on the countertop. So we want to move it to the other side of the room next to the coffee machine. You want to move the chair, the book, and so on. So the task can be specified in many different ways. It can be geometric. For example, we can say we want the toaster to be at coordinate 2, 3. Or it can be specified using language. For example, move toaster next to the coffee maker. Or we can provide an image of the goal instead. Okay, so I'm going to talk about a specific instantiation of rearrangement that a project that was led by Luca and Matt, and we call the project is about rearranging a room. So here is the problem. So there are two phases. There is a walkthrough phase that the agent roams around the scene and captures information about the state of the scene, where objects are located. And there's an unshuffle phase. So we temporarily remove the agent from the scene and make some changes to the scene. For example, we close the cabinet and we move the bread from one side of the room to the other side of the room. And then we introduce the agent back to the scene and ask the agent to undo what change in the scene. Right? So in this talk, all of the experiments that I'm going to talk about are done in AI2 Thor simulator. AI2 Thor is a simulator of indoor scenes. It has 120 different scenes covering 4 categories: bathrooms, bedrooms, kitchens, and living rooms. And the agents can perform different actions in these environments. For example, they can navigate, they can interact with objects, for example, turn on and turn off the light, or they can apply forces to objects to manipulate them and so on. So here's the overview of the system that I'm going to explain. So there is physics engine, Unity, that renders the images for us. We send the images to a neural network, and the neural network decides about the action. We send the action back to the game engine, and this loop repeats and repeats. Okay, so we introduced this data set that has 10,000 rearrangement, 120 unique rooms, about 1,200 objects that can open, for example, cabinets, microwaves, and so on, and about 1,900 objects that can be moved around in the scene. And this is different from traditional data sets in the sense that we do not provide step-by-step instructions for the agent. We just provide the initial state and the goal state for the agents. So why this task? Why should we care about this task? So this is a comprehensive task that subsumes skills such as navigation and object manipulation. It requires visual reasoning. We need to infer the differences between the current state and the goal state. We need to infer the state of the objects, for example. For example, is this cabinet open or is this closed? It requires manipulation of objects in cluttered environments. For example, an object cannot be moved if it's blocked by another object. So we need to remove the occluder first before reaching the object of interest. We need to reason about affordances. For example, we need to find a surface that can support the object that the agent is holding. And it requires navigation through complex environments while maintaining a persistent internal representation, where the agent came from, what actions the agent did, and what was what the consequence of those actions were, and many other challenges that's required to solve this task. So here is the model. I'm not going into the details of the model. The thing that I want to emphasize is just input and output. So the input is the egocentric observation of the agent. We also provide agent pose, and there's a bit that specifies if we are in the walkthrough phase or in the unshuffle phase. And the output is a sequence of actions among 84 possible navigation and interaction actions. We defined a number of metrics for this task. So one metric is success. If the episode is considered successful, if all objects are approximately in the expected position and state. Also, we have this, we call it person fixed. It's if we move a non-target object, it gets zero score. Otherwise, it will receive a percentage of, it receives a partial credit basically. And also we define this energy remaining gives partial credit if, for example, the agent moves the objects close to where they should be. So here's a plot for the results. There are some abbreviations that I need to explain. There's this IL means imitation learning. PPO is a form of reinforcement learning. ANM is a mapping module that's developed by researchers at CMU. And there are two types of tasks: one phase and two phase. One phase we assume during walkthrough, the walkthrough information is available to the agent during unshuffle phase. Two phase means walkthrough and unshuffle phases are separate, and the agent cannot directly access the information captured during walkthrough. So there are a number of observations. So first of all, the performance is quite low. It's about like 1% for the two-phase task, and about like 9% for one-phase task. And there's a big difference between the performance in two-phase and the performance in one-phase. Also, the RL method really struggle performing these types of tasks. Okay, here is a video that shows one of the successful episodes.
The agent is able to successfully open the drawer after spotting that it was out of place. It then picks up the vase and immediately puts it back after realizing it was already in the correct position. It then explores more around the room, trying to find if other objects are out of place. Soon it realizes that it must pick up the plate and move it across the room. The agent successfully rearranged both out-of-place objects to their goal configurations.
Okay, so we have a challenge and we have a leaderboard for rearrangement. We encourage everybody to participate in this to solve this challenging task. Okay, so while the rearrangement task was interesting in terms of reasoning and planning, we abstracted away object manipulation. If you notice in the video, when we issued the pickup action, the objects transported to the agent. So Kiana and the Thor team extended AI2Thor framework by adding a robotic arm, so we can do a more realistic object manipulation. So we call this framework manipulator. Object manipulation is an established field of research, but there are a few issues that we need to consider. So first is the speed of training. Look at this video. So this robot has been trained for 2-3 hours to perform this task, which is opening the door that's put right in front of the robot. While the algorithms for performing the task are quite impressive, but we cannot train for a long time because of the mechanical constraints of the robot. On the other hand, simulation allows us to perform lots of iterations of training, and because we can render like hundreds of frames per second, so we can easily try different learning algorithms and try different types of methods. The other issue that we need to consider is generalization. Usually for object manipulation, we assume the robot is next to a table and the objects are on the table. Sometimes Sometimes we put a green cloth on the table to make perception easier, but reality is different. So our robots should be able to manipulate objects and interact with objects in these types of scenes, that the objects are not necessarily on the surface in front of the robot. They might be at different heights, and the scene is visually complex, and we need to reason about the location of objects, the state of the objects, and so on and so forth. So simulation allows us to test the generalization capabilities of our models, because we can run our models, for example, in 100 different scenes simultaneously, and that's not quite feasible in the real world. The other issue is safety. For example, when we train a robot in the beginning, the robot can take random actions, and it can break the objects, it can damage the objects, it can damage itself, but there's no such issues in simulation. So we can safely train our models in simulation and then transfer the models to the real world. For example, here the robot picks up a glass bottle by mistake, it drops it on the chair, and the bottle breaks, but we can easily rewind this and continue our training without any consequence. Okay, so here is the robot that we designed. It's similar to the Kinova's line of work. It's basically, there's a wrist, there is some joints. We can move the arm up and down, so we can reach objects at different heights. We define a specific task for this framework. We are planning to extend that, but for now we want to move objects from a start location to an end location, to a target location. So here we want to move this pot from the stove to a location next to the sink. So there are multiple interesting manipulation scenarios. For example, sometimes the objects can be occluded. So here the tomato is behind the bowl. To reach the tomato, we need to move the bowl so we can reach that. Sometimes there's a tight margin. So there are objects on the shelf. So if we want to reach those objects, we need to be careful not to hit the shelf and not to hit other objects on the shelf. Sometimes objects are hidden inside other objects, and sometimes objects are contained within other objects, so it requires fine-grained manipulation so we can reach the object of interest. Okay, so the task has two stages. So the first stage is reaching the target, and the second stage is picking up the target object and move it to the destination location. So we define a success metric called success without disturbance. So here is what this video shows what it means. So here we want to pick up the salt shaker, but the robot by mistake touches the toaster and coffee machine and displaces them. So that's not considered a successful scenario. So here shows the successful scenarios. It picks up the salt shaker without touching other objects and moves it to the destination. So we have train test and train test scenarios. We have 20 scenes, 6 types of objects, 20 different instances per object category. And we also have zero-shot scenarios where we test the robot in scenes that it has never been before, and manipulating objects that it has not manipulated before. So this shows the results. So the front row, the purple bars shows the episode success without disturbance. The back row shows the pickup success rate. So pickup success rate is usually high compared to episode success, which means that the robot has a hard time moving the object to destination after picking up the object, because it can hit other objects and so on. And there's also it's also interesting that the depth information helps RGB, and the disjoint model, the model that performs the stages of the task separately, performs gets like zero performance. So that's that was kind of interesting, that the model that's trained for pickup is not necessarily a good model for success, even with fine-tuning for the entire episode. Also, we tested generalization to novel scenes and novel objects. So, for example, the back row shows pickup success. The middle row, the green bars show the episode success, and the purple bars show success without disturbance. It's interesting that the performance drops from when we consider disturbance when we compute the accuracy and performance. Okay, so here are some example videos of the agent. So the goal here is to move the tomato to another location in the scene. Here the agent is trying to pick up lettuce and move it towards the sink on the other side of the room. Okay, to conclude, embodied AI and interactive scene understanding require tackling a new set of challenges. The traditional pipelines that we have for computer vision might not be suitable for modern applications in interactive AI. We are very far from solving even simple embodied AI tasks, so that there are a lot of exciting challenges ahead of us. And finally, the work cannot be modeled perfectly in simulation. However, simulation allows us to first train our models fast. We can render hundreds of frames per second. So we can, today's state-of-the-art training algorithms require millions of iterations of training to learn something meaningful. So it might be hard to use them in the real world. Simulation allows us to better evaluate generalization of our models. We can test our models in many different scenes simultaneously. While it might be challenging for doing such experiments in reality, we can conduct reproducible experiments in simulation. For example, I have my own robot or my own lab, and somebody else might have their own robot and their own lab and lab setup and settings. So we cannot really compare the performance of our models, but simulation allows us to have a set of reproducible experiments, so we can measure progress easily. We can compare our performance and so on. And also, the last but not the least, simulation allows us to perform safe training and evaluation. And imagine, for example, training robots or self-driving cars in reality. So we need some form of simulation before deploying the models on the real robots. Okay, thank you for listening to my presentation.
Yeah, thank you. Thank you for the nice talk. I think it's very cool to see many interesting applications of embodied AI. Yeah, so I think there is a question in the chat box. The question is that in rearrangement, are the move shuffle objects always visible during the unshuffling phase? What happens if we place the object inside an, let's say, Almera? Yeah, is the agent supposed to explore them as well? Yeah.
So in this specific instance, because the problem is already super difficult, so we assume the objects remain visible after shuffling. So we did not. We can. I mean, our framework has the capability of, for example, we can hide objects. We can put them inside fridge. We can put them inside the drawers or cabinets. But to keep the problem simple, so we decided not to do that. And after shuffling, the objects are visible.
Okay. Yeah. Thank you. I also have a question. So, have you ever thought about moving ahead towards real things?
Yes, so we have a framework we call Robothor. It's basically we have apartments, like 14 apartments, and for those apartments we have the counterparts in simulation. So we modeled those exact apartments in simulation. I didn't have time to talk about that, but in another talk today, I'm going to talk about that framework. But we try to test our models in both simulation and the real world, and obviously there is a gap and between simulation and real. The models that are trained in simulation are not performing well in reality, and we are working towards some problems that some solutions to address this problem, so we can close the gap as much as we can.
Thank you. Yeah, I also think that the synthetic to real gap is also an issue if we rely on simulation. But we do need simulation to kind of learn the model pretty well, because it's hard to capture pretty good ground truth data from real things for this kind of complex task. Yeah.
Yep.
Yeah. Thank you. Yeah. Okay. So if there are any more questions, feel free to post it in the chat box. And Roozbehm, if you have time, you can also feel free to reply to them in the chat box. Yeah. Okay. Thank you.